Quantum mechanics challenges everything you thought you knew about reality, but not in the ways you've probably heard. The story isn't about consciousness creating the universe, or mystical connections across space. It's stranger and more precise than that. In 1927, electrons started doing something that shouldn't have been possible. Fire them one at a time through two slits, and they build up an interference pattern, like waves overlapping in water. But each electron hits the detector as a single point. Somehow, each one seems to go through both slits simultaneously, interfering with itself, producing a pattern that only makes sense if the electron exists in multiple states at once. Try to catch the electron in the act by measuring which slit it goes through, and the pattern vanishes. The electron picks a lane. The observation itself changes what happens, not because you physically bumped into anything, but because measurement entangles the electron with a detector that's connected to the environment. Information leaks out, quantum coherence gets destroyed, and what looked like a wave behaving in two places at once now looks like a particle following one definite path. This is the measurement problem. Before measurement, the mathematics describes the electron as a superposition, existing in multiple states simultaneously, according to the wave function. But when you measure it, you get one result. The wave function appears to collapse from many possibilities into one actuality. The equation that governs quantum systems doesn't include this collapse. It just evolves smoothly and deterministically. So where does collapse come from? Different answers to that question split physics into competing interpretations. The Copenhagen interpretation, dominant for decades, says don't ask what happened before measurement. Quantum mechanics describes correlations between measurements, not some underlying reality. Properties like position don't exist until you measure them. The wave function is a tool for calculating probabilities, not a picture of anything real. Many worlds says the wave function never collapses. Every possible outcome happens. The universe constantly splits into parallel branches where each possibility plays out. You see one outcome because you're in one branch, but other versions of you in other branches saw different outcomes. Everything that can happen does happen, somewhere in the multiverse. It's deterministic and simple in its postulates, but it commits you to an infinity of unobservable parallel worlds. Pilot wave theory says particles always have definite positions, guided by a real wave that evolves according to Schrödinger's equation. The electron really goes through one slit, but the pilot wave goes through both, interferes with itself, and guides the particle towards certain detector regions. It's deterministic and realist, giving you a clear picture of what's happening. But it requires faster-than-light influences between entangled particles and introduces hidden variables you can never measure directly. These interpretations make identical predictions for any experiment you can actually perform. That's why the debate continues. There's no experiment that settles it, at least not yet. You choose based on philosophical preference, which problems you think are most important to solve, which costs you're willing to pay. Quantum mechanics describes particles as excitations of fields that permeate all of space. An electron isn't a tiny ball. It's a localized ripple in the electron field. This framework, quantum field theory, handles particle creation and destruction naturally. Photons can become electron-positron pairs if they have enough energy. Particles and antiparticles can annihilate into pure radiation. The vacuum itself isn't empty, but filled with quantum fields, fluctuating around their minimum energy states. Entanglement is where quantum mechanics gets genuinely non-local. Prepare two particles so their properties are correlated, separate them by any distance, and measure one. You instantly know something about the other, not because a signal traveled between them, but because the correlation was established when they interacted. The particles don't have independent states. They share a joint state that can't be factored into separate parts. This sounds like action at a distance, but it isn't. You can't use it to send messages. The person measuring the first particle sees random results. The person measuring the second particle also sees random results. Only when they compare notes through ordinary communication do they see the perfect correlation. The non-locality is in the correlations, not in controllable influences. Bell's theorem proved that these correlations are stronger than any theory with local hidden variables can produce. Experiments have confirmed this repeatedly, closing every conceivable loophole. Nature really does exhibit quantum correlations that can't be explained by particles having definite properties determined in advance. Either reality is non-local, or properties don't exist until measured, or both. Decoherence explains why quantum weirdness disappears at large scales. Quantum systems are fragile. Let them interact with the environment, with air molecules or stray photons or thermal vibrations, and the delicate superpositions that produce interference get destroyed almost instantly. For a dust particle, this happens in less than a trillionth of a trillionth of a trillionth of a second. The particle still obeys quantum mechanics, but it decoheres so fast you never see quantum behavior. This isn't a solution to the measurement problem, but it explains why the problem seems to vanish in everyday life. Macroscopic objects are always decohering. Their quantum states become entangled with environmental states so thoroughly that interference. Effects disappear for all practical purposes. What looks like wave function collapse is actually information about the system leaking irreversibly into the environment. Thinking about quantum mechanics in terms of information clarifies some issues. Measurement isn't about consciousness or observation. It's about information transfer. When a quantum system interacts with a macroscopic apparatus, information about the quantum state becomes encoded in the apparatus, which then shares that information with the environment. The quantum information doesn't disappear. It spreads out into so many environmental degrees of freedom that you can't retrieve it. Quantum mechanics gets wildly misused outside physics. People claim consciousness creates reality because observation collapses wave functions. But observation just means interaction with a macroscopic system. A Geiger counter measures radiation without anyone watching it. Decoherence explains the quantum to classical transition without invoking minds. Consciousness has nothing to do with it. Entanglement gets misused too, invoked to explain telepathy or cosmic oneness. But entanglement is fragile, destroyed by environmental interaction almost immediately for any macroscopic system. Two people aren't entangled just because they met once. Their quantum states decohered instantly. Entanglement requires careful isolation, the kind you achieve in physics labs, not something that happens spontaneously between distant objects. Quantum mechanics doesn't give you free will through indeterminism, doesn't prove mysticism through observer dependence, doesn't enable quantum healing through intention affecting matter. These are misapplications of genuine physics, taking the theory's strangeness and extending it into domains where it doesn't apply. Quantum mechanics is strange, but it's strange in specific, mathematically precise ways that don't include most of what gets attributed to it. The measurement. The problem isn't solved. Decoherence explains why superpositions appear to collapse, but not why we experience one outcome rather than another. Interpretations differ on whether all outcomes occur, whether particles have hidden properties, whether questions about pre-measurement reality even make sense. These are open questions, not because the theory is broken, but because the theory works perfectly while leaving its deepest implications unclear. Quantum mechanics has been tested more thoroughly than any theory in history. It's never failed. Technologies from semiconductors to lasers to MRI machines depend on it. Every prediction matches experiment to absurd precision. But what the theory is telling us about the fundamental nature of reality remains genuinely uncertain. Maybe the wave function is real and describes parallel universes. Maybe it's a calculational tool that doesn't represent anything physical. Maybe particles have definite positions we can't know, guided by waves we can't see. These aren't questions physics has answered. They're questions physics has learned to live with, using the theory to make predictions and build technologies, while arguing about what it all means. That's the careful reframe. Quantum mechanics isn't mystical, but it is strange. It doesn't prove consciousness creates reality, but it does suggest reality doesn't have definite properties until measured, or that all properties exist in parallel worlds, or that properties exist but are hidden behind non-local waves. Which of these is true? We don't know. What we do know is that the theory works, that nature behaves this way whether we understand it or not, and that the universe, at its smallest scales, is genuinely unlike anything our everyday intuitions prepared us for. The math is clear. The experiments are decisive. The interpretation is contested. And maybe that's the most honest thing physics can tell you. Sometimes understanding how things work doesn't tell you what they are. Quantum mechanics gives you the how with extraordinary precision. The what remains, almost a century later, an open question. Thanks for exploring this with me today.